Okay, so serine proteases, or proteases in general, it's a big class of enzymes that, as we already mentioned earlier in class, like the point of proteases is to hydrolyze the peptide backbone, right? And they all catalyze the same reaction. They catalyze the hydrolysis of a peptide backbone. So if we're looking here, this that I label as the scissile bond, that's the bond that gets hydrolyzed. That's the reactive bond in the active site of the enzyme. Okay. Um, these enzymes are specific though. They look for very specific things. And all of them look for the sequence of amino acids usually just before the scissile bond, right? So just to the N terminus of our scissile bond, of our reactive bond. So here, if this is the bond that gets broken, what we are looking for is the identity of the side chain just before it, okay? So here, the enzyme trypsin looks for this side chain to be arginine or lysine, long chains with a positive charge at the end. Okay, and that table that I give you that looks intimidating on page, what is it? Page whatever it is on there, it looks intimidating, but that's the important thing about it, is it's so just before the reactive bond, it's looking for a lysine or an arginine. Chymotrypsin, just before the reactive bond, it's looking for big, bulky hydrophobic groups. And it specifies here phenylalanine, tryptophan, or tyrosine. For elastase, just before the reactive bond, we're looking for smaller things: alanine, glycine, serine, and valine. Okay, so the idea here is if you see a sequence of amino acids, like if you're given a peptide, which I give you a peptide in that following table, and in the sequence you find an arginine, trypsin will cut there. If you see a tryptophan, chirotrypsin will cut there. If you see a serine, elastase will cut there. Okay? And you can have multiple sites where things get cut, right? So let's say we have a sequence that is all right over here now. Let's say we have a sequence that's asp, phe, lysine, serine, arginine, alanine. Okay, so we have this sequence that's 6 amino acids long, and this is within the construct of a much larger protein. Okay, if we treat this peptide with trypsin, we know trypsin recognizes lysine and arginine. So everywhere you see a lysine or an arginine, it would cut. So you'd get a cut right here. You'd end up with a peptide that's asp, phe, lys. It would cut between the arginine and the alanine right here. So you'd have a second peptide that's serine, arginine, and a third peptide that's just alanine. You'd end up with 2 cuts, 3 peptides. If you treated it with chymotrypsin, here we're looking for phenylalanine, tryptophan, or tyrosine. Okay, we see a phenylalanine. So if you treated it with chymotrypsin, it would only cut in one place. You'd end up with 2 peptides, asp and phe. The second one would be lys, ser, arg, and ala. Okay, so that's the idea here. These proteases recognize specific things. Okay, and based on their specificity, you can predict what the product of hydrolysis would be. All right, but how do they do it, right? So what I'm trying to show here is, so this is the actual surface rendering of the enzyme trypsin. And what you see is that there's this big groove where this R2, the specificity target pocket, is. There's this big groove here that allows long chains to get in there. And at the end of that groove is going to be a bunch of negative charge. So trypsin recognizes lysine and arginine by having a specific interaction at the end of this channel, the end of this long groove, with that positive charge. Without making that interaction, the specificity, the affinity of the enzyme for the substrate is too low, and it won't bind for long enough for the reaction to happen. You can imagine with chymotrypsin, we're looking for big, bulky things. So we're going to have a big hydrophobic pocket that will allow big, bulky things to get in there, making strong London dispersion forces. which increases the affinity. And elastase is much smaller things, so that pocket's going to be a lot smaller. Okay, and if we look at this, that's really exactly what we see. For trypsin, here's our specificity pocket. So we have this big groove, this big hole, where the long chain of lysine or arginine can bind to, can interact with, and at the end, you have an aspartic acid that can make an ion pair. That ion pair is a strong intermolecular force that dramatically increases the affinity of the peptide for this position, right, for the enzyme. For chymotrypsin, it's a big hydrophobic pocket that has London dispersion forces between these two glycine side chains and the hydrophobic amino acids. For elastase, it's a much smaller pocket, right? So it's filled in with threonine and valine, so it'll only let smaller things sit there. Okay, so being able to think through things like that is a good, it's a good exercise, but it's also a good skill to have, right? So if you know the specificity of enzymes, then you can think through what the active site must look like to bind to specific things. All right, so this brings us to a really important idea in enzymes, right? Is identifying common themes in mechanisms, right? Because as I mentioned before, there are thousands and thousands of reactions that happen in the cell at any given time. But the really cool thing is they all break down into 6 categories. And within those 6 categories, we can further categorize reactions. And if we're good, we can identify themes. And one theme that occurs with these serine proteases, with trypsin, chymotrypsin, and elastase, is that the reaction, the mechanism in the active site, is identical. Okay, and it's really kind of cool how it happens. So these are called serine proteases because they use serine as a nucleophile to initiate the reaction. Okay, and again, I mentioned on Monday that I have a video posted that I encourage you to watch because I go through it very slowly and identify the steps that are happening along the way. But so the idea here is that this serine is positioned at the scissile bond, right? So here's the serine that we see right here. This is positioned right at this scissile bond. So this is the active site of trypsin, and we know that because we see this arginine here. All right, the arginine is the amino acid adjacent to the scissile bond. The serine is the initial nucleophile, which is interesting because serine is not easily deprotonated. It's not easy to activate that hydroxyl group as a nucleophile, right? It's hard to deprotonate alcohols. So the way that it works is that it is in hydrogen bond contact with a histidine, which is in turn in hydrogen bond contact with an aspartic acid. So this is called a catalytic triad. 3 amino acids that work together to serve one function. Okay, so in this triad, ultimately what happens is, right, so you can imagine that there's this hydrogen here on the alcohol of the serine. The lone pair on the aspartic acid reaches out, it pulls a proton off of the histidine. That impacts the resonance within the histidine, within the imidazole of histidine, which then shifts over and allows this nitrogen to deprotonate that serine. Okay, it might be easier to see here. The oxygen deprotonates the nitrogen of histidine, which then impacts the resonance here, and picks up that proton. Right, so this proton right here on serine is electronically linked all the way back to that aspartic acid. So the aspartic acid draws protons, draws electron density through that imidazole chain and ultimately allows the serine to be deprotonated. So it's a really interesting way of activating serine to be a nucleophile. Can you all see that? Okay. So we activate serine to be a nucleophile, and once we activate serine to be a nucleophile, we can then make nucleophilic attack on the carbonyl nitrogen of the cis-aryl bond. Okay? Lots of words, let's show it. And again, this entire mechanism is on the next page of your activity. So I show you every step along the way, and I ask you to describe it. Okay, so okay, so I'm just going to kind of abbreviate here. So the triad here, so this is where the aspartic acid and the histidine are. Okay, the idea is that this triad is linked with that hydrogen. Okay, here's our peptide bond that gets broken. So the way this gets initiated, the way this process starts, is the catalytic triad effectively deprotonates that serine, making it a good nucleophile. The serine gets activated as a nucleophile because of how it's electronically linked to that aspartic acid through this histidine. Okay? Once it's activated as a nucleophile, it has a negative charge, and it can now serve as a nucleophile to attack the carbonyl. The electrons in the pi bond between the carbon and the oxygen flow up onto that oxygen. This makes an intermediate. I think that I show it here. Yeah. All right, so this forms this important intermediate that we see on the right here. The intermediate is tetrahedron, right? That carbon went from sp2 to sp3 hybridized. It went from trigonal planar to tetrahedral, and the tetrahedron now has an oxyanion. Okay? What's cool about this enzyme and about lots of other enzymes that do similar chemistry is that they position a positive charge where the oxyanion forms. Right? So if we look closely here, what we see is that this oxygen starts off at this position right here. Once the serine, our nucleophile, attacks that electrophilic carbon and we create our intermediate, that intermediate, the oxygen shifts to this position. And the fact that the enzyme is presenting this positive patch, right, that those NH bonds, like those NH vectors, the hydrogens have a partial positive charge, that partial positive charge stabilizes the negative charge from the oxyanion. So that decreases the energy of the transition state. That makes the reaction faster. Okay, and then we can get the collapse of this pocket, right? So we get collapse, and in this case, we're going to release the NH. So we've broken that bond. Does that make sense? Everybody seeing it? Is anybody not seeing it? You're not seeing it? Okay, so I guess what I'm going to suggest is work through, I'm going to borrow this for a second, work through and look at this page of your activity. It walks through every step along the way, okay? Work through it. If it doesn't make sense as you're working through, I'll come around and we can talk about it, okay? There's that as a resource. There's also, if you go online, the video I made, I think I do a much better job in the video than I can right here. So I encourage you to watch that, okay? And of course, I'll answer any questions you have as I walk around.